Hello, and welcome to the second video in section 1.3 of your book. This video, we will cover matrix algebra and the matrix form of a linear system. Let's start with matrix algebra. So as you already saw in your pre-assignment, the way to add matrices, say you have two n by m matrices, so n rows, m columns for the first one, n rows and m columns for the second one, and you want to add them together. Well, it's nothing crazy. You just add the entries. Okay, so you have another matrix of the same size, but now the entries are just the added entries from the matrices you're adding. And I don't think your book explicitly says this, but no, you can only add matrices with the exact same dimensions. And what you get out is a matrix with the exact same dimensions. So no adding a 2 by 3 matrix to a 50 by 50 matrix. They have to be the same dimensions. Okay, and you've seen some examples in the pre-assignment, but what I want to say now is that this definition of adding matrices makes sense given what we already know about adding vectors. So, we can think about vectors as just a column matrix. So, for example, when we are adding vectors, now let's think of them as column matrices. Well, to add vectors, you add the components. And there's like a geometric reason for this. If we're like adding arrows in tip to tail addition, then adding the two arrows together and the new arrow you get is what you get from adding the components. So if these were just thinking purely in like vectors before you ever took this class, we would say, all right, this vector plus this vector is just 2 plus 5, 7, plus 1 plus 2 is 3, and 1 minus 2 is minus 1. Okay, the matrix version of adding gels with what we already would have done if we hadn't seen this definition, but we're just adding matrix column vectors. This also makes sense given how we add equations. So remember, equations often correspond to a row and a matrix. And so if we're adding two equations, say we're adding the equation 2x plus y equals 1 and 5x plus 2y equals negative 2, then when we're adding those two equations together, we would group like terms and we would say, okay, well, the new equation that we get is 2x plus 5x. We'd say it's 7x plus 3y equals minus 1. And so that's exactly corresponding to how we add row vectors or row matrices. So this should tell you that there is no other way we could consistently define adding matrices, given what we already know about the correlation between matrices and vectors and the matrices and equations. So, okay, we should feel rock solid about this definition. Another definition you saw in your reading was scaling matrices. So this is how do you multiply a number times a matrix? So, all right, nothing too exciting. You just multiply each entry by the number. So that's how you multiply a matrix times a number. And I want to emphasize again, this makes sense given how we were scaling vectors before we ever came to this class. So again, for example, we have a vector and 2, 1, 1, and if we think of it as an arrow, we want to scale that arrow, make it 3 times as long. Well, we have to multiply each coordinate by 3. And so when we defined scaling of vectors, it was just, all right, multiply each component by the scalar. And we would get here 633. So good, it should be this way. And again, same with equations. All right, you have some equation. I mean, we've done this a bunch of times already in this class. You take an equation, multiply it by a scalar. What do? You scale every single term. So for example, we have some equation 2x plus y equals 1. If we multiply the equation by 3, we're just multiplying each of the coefficients by 3. So then we would end up with 6x plus 3y equals 3. So again, given how we were already doing these things before we started this class, there was no other way we could have defined multiplying a matrix by a number. It had to be this way in order to make sense with what we already knew. All right, So let's talk about multiplying matrices. Oh, actually, hold your horses. Geez, trying to get ahead of yourselves here. It's actually not what you think. So you are probably thinking that multiplying one matrix times another, well, you just multiply the entries, kind of like how when you added two matrices, you added the entries. And it's not that. That is a thing. Like what, this entry by entry multiplication, it is a thing. It's called the Hadamard product, but we will not be using it in this class ever. So, okay. How do you multiply matrices then? Well, it's hard to define an operation when you don't even know what the point is. And so let's try to figure out, like, why would we even multiply matrices? Now, I know we didn't ask this question back when we were adding and scaling them, but we already were kind of forced into definitions. So, all right, let's try to force ourselves into a definition of multiplying matrices. And let's do that by thinking about vectors. So, how do you multiply vectors? Well, back in the good old days of vector calculus, we actually had two ways to multiply vectors. This should give you an idea of why maybe it was too hopeful to think there'd be an easy way to multiply matrices. Okay, so suppose we had two three-dimensional vectors. One product we had was the dot product. Honestly, my preferred of the two products we learned in vector calc. The dot product, if you remember, is you say vector v dot vector u. What you would do is you would kind of do this entry by entry multiplication. You do v1 times w1, v2 times w2, v3 times w3, but then you'd add them all together. And so you'd end up with a number. And it might not have been clear to you at the time you took vector calc, like why you would define the product that way. Like, why would you just add them up in the end? Well, it was motivated by geometry. It's one of those things where, mathematicians were doing a lot of calculations. Say, all right, you've got a vector and you want to find the length of the vector. Well, they'd say, oh, the length of the vector, well, from the Pythagorean theorem is something that ended up, we call it now v dot v. But at the time, you would just, write it out as v1 squared plus v2 squared plus v3 squared, and then take the square root. And if that was the only place it showed up, I don't know if it had gotten its own name. But also when calculating the angle between vectors, maybe you'd calculate this like right-hand side and then recognize, oh, that left-hand side, that's just that same kind of operation up here. We're seeing that again. And similarly with projection, something that's hugely important in applications is you want to find, okay, you've projected vector v onto this vector w, and you want to know how long that component is. Oh, you see this sum coming up again. And you see it enough times in geometry and you start giving it a name. And so we gave it the name of the dot product. But yeah, this isn't the only product that we saw in vector calc. There's also the cross product. Something vector v cross vector w is, well, it's a vector, but it's something horrible like that you're almost guaranteed to make a mistake in if you are calculating this thing by hand. Really, really don't like calculating the cross product. And where did that come from? Well, it was also motivated by geometry. Here, the motivation was actually in finding an orthogonal vector. So if you have like some vector v and some vector w, and you just, using the dot product, tried to find an orthogonal vector, this is the first one you would calculate. And to everyone's great relief, we will not touch the cross product in this class. You're welcome. And now in linear algebra, we have a concept of the dot product as well, and it's the same. So, all right, you take two column vectors, dot them together. You do it like it was written as, like you would have in vector calc. So it'd be 2 times 1 plus 0 times 2 plus 1 times 3 is 5. And similarly, okay, you have a row vector times a column vector. Same thing, just multiply the entries and add them up. And so, no, in linear algebra, when we take the dot of two vectors, it can be a column vector times a column vector, or a row vector times a row vector, or a row times a column times a row. Either way. So it's not sensitive to whether you're multiplying rows or columns. So the dot product is going to be important for how we define matrix times vector multiplication. And before we define matrix times vector, let's motivate the definition we end up with a little bit. So let's say we have this linear system here. And all right, let's organize our information. Let's find the coefficient matrix. So we write that as, all right, 5, 2, 3, 2, negative 1, 14, 4, 6, 3, negative 3 ends up here. And now I'm going to do something a little, I guess, maybe that you haven't seen before. I'm going to write it in terms of its rows. So I'm going to write each row, think of each row as being its own vector. So this row 1 vector would be 5, 2, 3. This row 2 vector would be 2, negative 1, 14. And this row 3 vector would be 4, 6, negative 3. And so we kind of think of this coefficient matrix as like 3 row vectors stacked on top of each other. All right. Now we've got something we'll call the solution vector, or, it's also can be called the variable vector, but it's a column vector where the entries are our variables. And I'm going to follow your book, and it's just very standard to call this solution vector X. Just X with a vector arrow over it. And now, notice. Let's look at equation 1. 5x plus 2y plus 3z equals 1. That is 5x plus 2y plus 3z equals 1. That's just row 1 dot x vector equals 1. Similarly, equation 2, 2x minus y plus 14z equals 4. That's row 2 dotted this with the x vector equals 4. And also with equation 3, it's row 3 dot the solution vector equals 2. That gives us our third equation. So, okay, we are seeing the dot product. We're recognizing the dot product showing up in a linear system. So let's define the matrix vector product this way. Take an n by m matrix and write it in this like row form where, okay, we've got, since it's an n row matrix, so we'll have n row vectors. And each of these row vectors has to have m components or m columns because it's an m column matrix. So, okay, we've got our n by m matrix, n rows with m entries each. And then we'll take some column vector, call it x, and it has x1 all the way down to xm. So the number of rows or entries or components in this will be the same as the number of columns. So the number of components equals the number of columns. If we have matrix and vector of this form, then we define the matrix vector product, call it AX. Right, I'm just rewriting A and rewriting X in this way. This is defined to be the vector you get by here. So the entry, say the first entry is W1 dot the vector X. The second entry would be W2 dot this vector, all the way down to Wn dot this vector will be the last entry. And notice this is a column vector with n components or rows. So a matrix times a vector gives you a vector, not a matrix or a number or something like that. So let's do an example. So, all right, suppose you have a 2 by 3 matrix, then our vector that we would multiply it by should be a 1 by 3 vector. So, all right, matrix A, that'll be our vector X. And what is the product equal to? Well, at the first entry, we dot this first row times the vector. So it'd be 3 times 1 plus 2 times 1 plus 2 times 3. And then the second entry is going to be the second row dot this vector. So 3 times 1 plus 1 times 0 plus 2 times negative 1. Add these all up and you get the vector 11, 1. And that is the product A times X. So now the buildup, this is all to give us, well, I mean, I guess finding the matrix vector product, defining that was a big deal, but it was all motivated by linear systems. So let's end with this concept of the matrix form of a linear system. So, okay, we've got this linear system from before. Look at its coefficient matrix, the solution vector, and now let's think about this column vector, the vector or constant vector, the vector of these, the right-hand sides, 1, 4, 2. Then we can write this linear system as a matrix vector product kind of in that form. So where we take the matrix A, multiply it by the vector X, and get the vector B. In this system, here's our coefficient matrix, here's our solution vector, here's our constant vector. And yeah, if you do this matrix product, you end up with this system, or with this identity, this matrix equals that matrix, or that vector equals that vector. And yeah, you set the components equal, and there you go. You've got your linear system. So this will be really helpful because this is, yeah, how computers think about linear systems, and it'll make finding solutions, but there's a lot going on. It's conceptually very rich. We will be using this form a lot. So once more for those in the back, you can write a linear system with augmented matrix A and vector B. So A is the coefficient matrix, B is the right-hand side. You can write it in matrix form as A times the solution vector equals B. And there we go.